Hey everyone, and welcome to this explainer. Okay, so if you've spent literally any time looking at NMR spectra, you already know the absolute basics of spin-spin splitting. But today, we are pushing way past those standard boundaries. We're going to explore long-range coupling, specifically how allylic, homoallylic, and homopropergillic interactions actually work in the real world. Let's dive right in.
To kick things off, I want you to try and imagine something. Imagine protons communicating over distances that, well, completely defy the standard rules of NMR spectroscopy you might already know. Normally, we think of protons talking to their direct neighbors, right? Those separated by just 3 bonds. But what happens when protons talk across 4, 5, or even 6 bonds? The signals don't just disappear into the void. They actually find a brand new way to travel.
So, here's our roadmap for today. We'll start with what happens beyond the classic 3-bond rule, uncover the secret of the pi-electron bridge, and then systematically explore allylic, homoallylic, and homopropergillic coupling.
All right, section 1, beyond the 3-bond rule. Let's quickly anchor ourselves in what we already know, right, before we completely break those rules.
Let's compare these two interactions. On one hand, we have standard vicinal coupling. That's your 3J. This is the typical everyday interaction between hydrogens on adjacent sp3 hybridized carbons. It's strong, it's common, and it usually gives a coupling constant of about 6 to 8 Hertz. But on the flip side, we have long-range coupling, denoted as 4J through NJ. Now, these interactions are much smaller, usually hovering between 0 and 3 Hertz. And here's the catch. They don't happen automatically just because the atoms happen to be in the same molecule. Instead, they require very special structural bridges, like pi-electron systems or incredibly rigid spatial arrangements like a W shape.
There's a really crucial concept here from our source material, and it goes like this. Long-range couplings are communicated through specific overlap of a series of orbitals, and as a result, have a stereochemical requirement. This is huge. It means we aren't just counting bonds drawn on a flat piece of paper anymore. We actually have to think about the molecule's full 3-dimensional geometry and how its actual orbitals align in space.
Moving on to section 2, the pi-electron bridge. So if these protons are supposedly too far apart for a standard bond interaction, how on earth are they sending these signals?
Think of the pi electrons in a double bond as acting kind of like a telecommunications wire. The spin information from a hydrogen atom isn't just magically jumping across empty space, it is actually being transmitted straight through the electron cloud of the pi system to a hydrogen on the entirely opposite side.
Let's actually break down the mechanics of this pi-electron bridge. The orbitals themselves act as literal conduits for the spin information. Because of this, everything depends heavily on the stereochemical 3D geometry of the molecule. For the signal to travel, there absolutely must be a specific spatial overlap between the s orbital of the carbon-hydrogen bond and the pi orbital of the double bond. If the molecule twists into the wrong shape, well, the connection is literally broken, and the protons can no longer hear each other at all. Section 3, allylic coupling explained. Now that we know exactly how that bridge works, let's dive into our very first specific category.
We call this allylic coupling. It's a 4-bond or 4J interaction. Basically, it occurs when the pi electrons of a carbon-carbon double bond actively help transmit spin information from a hydrogen directly on the double bond, the alkenyl hydrogen, to a hydrogen on the adjacent carbon, the allylic hydrogen. Think about the physical reality of this coupling. For the signal to actually be transmitted, the actual s orbitals of those carbon-hydrogen bonds must physically overlap with the pi system. It's all about that side-by-side connection. Because it completely relies on this physical overlap, allylic coupling follows some pretty strict rules. You get maximum overlap and therefore the strongest coupling, hovering around 3 to 4 Hertz, when the allylic CH bond is aligned perfectly parallel with the plane of the pi bond. On the other hand, you get minimum overlap when the CH bond is exactly perpendicular to the pi bond. When it's perpendicular, you are essentially cutting the wire, and the coupling drops straight down to basically 0 Hertz. Any angle in between, that just gives you partial orbital overlap and intermediate coupling values. All right, section 4, homoallylic interactions in alkenes. Let's see how all of this builds when we zoom out even further, extending our view to a 5-bond distance.
This brings us to homoallylic coupling, a 5J interaction. Here, the coupling is extending across a double bond or an alene system. But because we are getting further away, separated by a whole 5 bonds now, the physical requirements for these protons to actually communicate become even stricter. It becomes highly, highly dependent on precise structural constraints. In your standard open-chain acyclic alkenes, this 5J coupling is honestly barely noticeable because the molecule flops around way too much to maintain that perfect orbital overlap. But homoallylic coupling suddenly becomes prominent in highly constrained systems. Think of rigid molecules like 1,4-cyclohexadiene or allenes like 1,1-dimethylalene. Because these rigid rings or allene structures force the molecule into the perfect locked-in geometry, the orbitals overlap consistently, which allows the 5-bond interaction to reach about 3 Hertz. That's pretty impressive for 5 bonds away. And that brings us to section 5, alkynes and homopargylic coupling. Time to swap out that double bond for a triple bond and watch the rules change entirely. Here's a really fascinating contrast for you. As we just discussed, homoallylic coupling in alkenes is incredibly rare in flexible, acyclic systems because it relies on such a highly specific conformation. But look at homopropargylic coupling in alkynes. It is almost always observed in the proton NMR spectra of internal alkynes. So you have to wonder, why are triple bonds such incredible spin conductors compared to double bonds? Well, the secret is entirely in the geometry. An alkyne has a triple bond, right? Which means it has 2 pi bonds perpendicular to each other, creating a literal cylindrical pi system. Because this electron cloud is a complete cylinder around the carbon-carbon axis, the adjacent CH bond doesn't have to be locked into one perfect angle. Almost any rotational conformation of that adjacent CH bond is going to partially overlap with that cylindrical pi system. The telecommunication wire is essentially always connected, no matter how much the end groups are rotating. Let's put the numbers side by side to really get a feel for this. Allylic, a 4-bond coupling, typically gives us 0 to 3 Hertz. Homoallylic, a 5-bond coupling in alkenes, also gives 0 to 3 Hertz, but remember, only in very rigid systems. But homopropargylic coupling, which spans 5 or even 6 bonds, often yields coupling constants greater than 3 Hertz. Because of that incredible cylindrical pi bridge we just talked about, these alkyne interactions absolutely punch well above their weight class, maintaining strong communication over very long distances.
So what is the big takeaway from this explainer? It's that analyzing an NMR spectrum isn't just a simple game of counting the bonds drawn on a flat 2D page. It is all about visualizing the molecule as it exists in 3D space. Coupling is heavily dependent on orbital overlap, stereochemistry, and all those hidden electronic bridges that tie a molecule together. So the next time you're staring down a complex chemical structure, ask yourself, are you ready to see the hidden 3D electronic bridges in your molecules? Thanks for joining me for this explainer, and I will see you in the next one.